Hi everyone, hope you guys are doing good today. Today I am going to start a new chapter. This chapter based on the normal distribution. This normal distribution is really important in statistics because we use this normally distributed concept almost everywhere. So let's go through this. First section is to introduce this normal distributed variable. Okay. First, I need to tell you that what is a density curve. You have seen this density curve before. This density curve is a curve which represent the distribution of a variable. So it is shape, and that we can frequently identify the shape of the distribution with a smooth curve. Smooth curve means there is no lag or there is no gap between 2 points. It should be a smooth curve. This kind of curves we call density curves. As you remember, if we draw a histogram, then we can draw this kind of curve, a smooth curve. Okay, I'll show it here. If I draw okay, if I draw a histogram, this is a here it is a frequency. So histogram, it would like this. Okay, this is an example histogram. When I merge these central points of each bar, I can draw a curve something like this. Okay, a smooth curve. See, there is no lag or there is no gaps in this line. So this kind of curve we call smooth curve or density curve. Clear? In theoretically, the density curve represents the distribution of a continuous variable. Okay, why continuous? Because in this case, see, this curve, if you consider curve something like this curve, it has values in this axis. Let's say this is x-axis. So each x value, it has a y value or it has a value, right? So in between these two intervals, 2 points, there is many points. So that's why it is continuous, because each and every point we have a value in this curve. Okay, but most of the time, if we have a discrete case, suppose that this x is a discrete value, we approximate the distribution of a discrete variable. So at that time, if we have a discrete variable, we approximate it to a normal distribution or density curve. Okay, a density curve. Okay, let's see what we are doing in this section. So with this density curves, there are two properties. Density curve is always on or above the horizontal axis. So please remember that this is my horizontal axis. Always this density curve on or above this horizontal axis. Okay, it never goes down. It never goes down of this axis. The second property is total area under this curve. Total area, which means this colored area, total area under this curve is equal to 1. Okay, area in between this curve and this horizontal line. Okay, area in between this curve and this horizontal line is equals to 1. Those are the two prominent properties in this density curve concepts. Okay, so this area, it doesn't matter where we start or where we end, the area under this curve is 1. Okay, See, as I mentioned in last time, this area, this light blue color area equals to 1 area under the curve. Okay. Okay. Variable and their density curves. A variable with a density curve, the percentage of all possible observations, we can mention the area under the curve. Okay, simply if I have a curve like this area from here to here, let's say this one is A, this one is B. So between A and B, the percentage of all possible observations I can mention by using the area between A and B. Okay, that's what they have mentioned here. A variable with a density curve, percentage of all possible observations, percentage of all possible observation of the variable that lie within any specific region. My specific region is A and B. Okay, the corresponding area under the density curve expressed as a percentage. So percentage equals to what? Percentage equals to area under the curve. Under the curve within the given this specific range, within the given range. Okay, so percentage is equal to the area under the curve within the given range, like A and B. Okay. Okay, these three figures show you how it works with different areas. If I consider my area from left end to this point C, this area to the left, the percentage of all possible observations of the variable that lie to the left of C, which means area from left end to C. Okay, area from left end to C. So expressed as a percentage, we can express this area as a percentage. Okay, then if I consider area from D to right hand side, percentage of all possible observations of the variable that lie to the right of D, to the right of D. Okay, this area expressed as a percentage. So area to the right. So please try to memorize these words. First one, area to the left of C. Okay, area to the left of C, which means from left to C position. Say next one is area to the right of D, which means area from D to right hand side. Okay, next one is the percentage of all possible observations of the variable that lie between A and B equals their area expressed as a percentage between 2 points. So we can mention area between 2 points as well. Okay, area to the left of C, area to the right of D, and area between. So these are the three major cases that we are considering in this section. Okay, we have an example. the area under the density curve that lies between, okay, we have this keyword between 3 and 4 is this much, 0.387. What percentage of all possible observations of the variable lie between 3 and 4? So what is the observation? What's the percentage? So this is the density curve. Here we have 3 and here we have 4. So they are telling that this is the density curve area, okay, between 3 and 4. The value is 0.387. Clear? This one. So we need to find the percentage. So it is easy, you can simply multiply this area by 100. So area multiply by this multiply sign, multiply by 100, you can have the percentage. Okay, area multiply by 100, you can have the percentage. Okay, second one, the area under the density curve to the right. So to the right of 2 is 0.762. So when you read this kind of question, please try to draw a picture until you are familiar with these concepts. Okay, to the right of 2, to the right mean whatever from 2 to right hand side. This value is 0.762. Got it? What percentage of all possible observations of the variable exceed 2? Okay, exceed 2. So percentage which exceed 2, which mean percentage of this value, right? So 0.762, as I mentioned before, you have to multiply by 100, then you have this value 76.2. Okay. Okay, next one. What percentage of all possible observations of the variable are at most 2? So at most 2. What percentage of all possible observations of the variable at most? Okay, at what is mean of at most? At most mean maximum value is 2. Maximum value that you can reach is 2. Okay, so you need this area from left to 2, from left to 2. From the previous part you have figured it out, this one value exceed the percentage which exceed, oh let's say area, let's talk about area. Okay, area 0.62 is belongs to exceed the 2. Okay, exceed 2, the area is 0.62 or 0.762. Okay, so you know what is the value belongs to this area, it is 0.762. Okay, so what is the total area under the curve? Total area under the curve, it is equals to 1. Okay, so you know the total area under this curve is 1, and also you know the area which exceeds 2. So what you have to do, 1 minus area exceed 2, this is area exceed 2 from part B or question part 2. Then multiply that value by 100 so that you can get this. Clear? This is how we are dealing with areas under the curve. Okay, normal distributed variable, this is really important because most of the time you will see this term, normal distributed variable, normal distributed, this kind of words. So a variable is said to be a normally distributed variable, or it has a normal distribution if that distribution has the shape of a normal curve. If that distribution has a normal curve, we call it normal distributed. What is a normal curve? Do you remember this bell shaped curve? I'm sorry, this little bit not smooth, but this is the normal curve, bell shape. Do you remember that? Bell shape, perfect bell shape. So this bell shape we call normal distributed. Okay, so if we have this normal curve, we call that variable is normally distributed. Okay, frequency, relative frequency table. We have this relative frequency table. They have given different height categories, so or height groups. So they have mentioned their relative frequencies here. Total is 1. Yes, you have this total frequency, which means it is let's say simple length, whatever. So now what you have to do, you have to draw a histogram. Okay, according to these height classes, when you draw the relative frequency, you will see this kind of histogram. So now they have drawn a density curve by connecting these points. So in this blue color line, see, I'm drawing on that color, blue color line. uh, it is a bell shaped curve. So this is a normally distributed variable, so it's a normal curve. Okay, so for now, forget about this part. Normal curve mu 64.4, sigma 2.4. So I'll explain that later. Just focused on the shape. Okay. Okay. So normal distributed variables and normal curve areas. Same as the concept what we will learn a few pages before. If we have this normal curve, area under this normal curve represents the percentage. Area under this curve represents the percentage. So if we have this normal curve, which means that variable is normal distributed variable. Okay, a normal distributed variable, the percentage of all possible observations that lie within any specific region, specific range, equals to the corresponding area under it associated normal curve. Okay, expressed as a percentage. So again, percentage equals to this area. Okay, percentage equals to this area, not direct equal, but percentage equals area, which means you have to multiply that area by 100. Okay, that percentage we use this area. Okay, that percentage we mention by using this area. This result hold approximately for variable that is approximately normal distributed. Okay, normal distribution is determined by parameters. Actually there are two parameters. Okay, normal distribution has a two parameters, mean mu and standard deviation sigma. This we call mu, and this we call sigma. Okay, it has two parameters. This is in another word we call mu is the location parameter and sigma is the shape parameter, but you don't need that terms. Just focus on what is this mu and sigma. Mu is the mean of that distribution and sigma is the standard deviation. Okay, two normal distributed variables have same mean and same standard deviation, then they must have same distribution. If two normal distributed variables have same mean and same standard deviation, which means mu and sigma are same, then they must have the same distribution. Okay, they must have same distribution, because this mu and sigma is the major component in this distribution. They are the guys who change this distribution. Okay, if they are same, then those two variables have same distribution. That's the idea behind it. Okay, normal distribution is symmetric about center at the mean of the variable, and is spread depends on the standard deviation of the variable. Okay, which means this normal distribution is symmetric about and centered. Okay, so this that's what we call mu is location parameter, sigma is shape parameter. Okay, sigma actually sigma shift sigma is the body, like the shape. it changed the shape of the curve. Mu is the guy who shift the curve horizontally. Okay, that's they have mentioned here. If a variable of population is normal distributed, then the only one variable under consideration, we say that population is normal distributed. Okay, population is normal distributed. This is important case. If we know that our population is normal distributed, then only one variable under consideration, we say that population is normal distributed. If variable of population is normal distributed, variable of a population normal distributed, and the only one variable, under consideration, we say population is normally distributed. Okay, if the variable distribution is shaped roughly like a normal curve, then we say variable is approximately normal distributed. Okay, so this approximation also work with this section, because sometime we need to approximate. If we see that shape roughly like normal curve, then we approximate it to normally distributed, so we say it is roughly normal distributed. Okay, there are few properties. This normal distribution is bell shaped. Okay, it has a bell shaped curve. It has a bell shape, so we call it bell shaped curve. And centered at mu, this is my mu value, mean, centered at mu, close to the horizontal axis, outside the range from mu. Okay, these are very close. In this point, I'll keep a small gap because otherwise you cannot see that. These points, this curve is very close to this horizontal axis. So these points we call mu. From left side, mu minus 3 sigma. From right hand side, mu plus 3 sigma. Do you remember this 1 sigma, 2 sigma, 3 sigma rule? We were I think we talked about this in previous chapters. Okay, uh, 1 sigma, 2 sigma, 3 sigma, they have different percentages that they represent the this much observation, this much observation, something like that. Okay, so this is that idea. Okay, if the random variable x, okay, my random variable is x, we call is normal distributed with mean mu and variance sigma, with mean mu and variance sigma. Actually this is gonna be not variance, this is gonna be, you can use standard deviation. Standard deviation, we can use variance as well, but in this section we don't use that variance, that word variance we don't use that much, we use standard deviation, so don't worry about that. Okay, don't worry about variance or standard deviation, normally it's standard deviation. So we can denote this by x has, this mean has. Okay, x, how this how we explain this, x has a normal distribution with mean mu, and standard deviation sigma. Standard deviation sigma. Okay, that's how we represent a normal distributed variable. X has a normal distribution with mean mu and sigma. Clear? And this normal distribution has a density function or density curve. By using this function you can get the value. Okay, this is the probability density of x. Fx is the, which means we denote, how we denote the function using this. Okay, 1 over square root of 2 phi sigma squared e to the power negative x minus mu squared over 2 sigma squared. Okay. But you don't need to worry about this formula. Okay, we don't need to use this formula, but just keep an idea. Probability density function of x is this one. Okay. Okay, standard normal distribution. Standard normal distribution or the standard normal curve, which means if my mu, do you remember this notation, is equal to 0 and let's say sigma, which means this notation equals to 1. I have a variable which has a normal distribution with mean 0 and sigma is 1. Then we call this is a standard normal distribution, or this x has a standard normally distributed, this x no, standard normal distributed, or x has a standard normal curve. A normal distributed variable having mean 0 and standard deviation 1 is said to have the standard normal distribution. It associated with its standard normal curve. Okay, see in this graph, in this picture, see mu is 0, but here by looking at this you cannot say what is the sigma value, it doesn't matter, but mu is 0. So if I have a standard normal curve, or if I have a standard normal distribution, standard normal distributed variable x, we denote like this: normal distributed mu 0 and sigma 1. Okay, this is a special case. This gives you a perfect bell-shaped curve. This is a perfect bell-shaped curve. Standard normal distributed variable. If we have any other distribution, like for an example, if you have this kind of distribution, you can convert that into this standard normal distribution. Standard normal distribution by using this. We call this variable c, it doesn't matter what you are considering. Standard version of normal distributed variable, this is also normal distributed, okay, but we need standardized normal distributed. We need to standardized version. So what we have to do, you have to consider each observations x minus mean of the distribution divided by standard deviation of the distribution, so that you can convert everything or every observation into a standard normal distribution. Okay, so how we will see how we use this concept to solve problems, or how we deal with numbers. Okay, standard normal distributions, there are three normal distributions, sorry, they are not standard normal distributions, they are normal distributions. So there are three: green color, red color, and this yellow color. First one, consider the green color normal curve. You can see they have mentioned it has mu -2. Okay, see, mu -2, and sigma is 1. Here mu is 3, see, center is 3, mu is 3 and sigma is 1/2. In this case mu is 9, okay, you can check, center is 9, sigma is 2. Now can you see the relation? See here, mu is -2, so graph here, mu 3, so graph comes to right hand side. Then again third one, mu is 9, graph shifted to 9. See, mu shift the graph or shift the curve. When you consider sigma, see here it is 1, it's like this pattern. Here it is 1/2. So when it's 1/2, this become little bit shrink. Okay, its width comes to smaller. When you consider sigma is 2, which means it's higher than these two, it's like spread. Okay, so that's why we call mu is the location parameter and sigma is the shape parameter. So sigma controls the shape of this distribution. Okay, anyway, it doesn't matter about the pattern, or it doesn't matter about the shape of this normal distribution. You can convert this normal distributions into standard normal distribution, standard normal distribution. Okay, by using this mechanism, by using this formula. Do you remember that this formula? They have mentioned the same formula. See, x minus mu divided by sigma. Here it is mu is negative 2, sigma is 1. So each cases you can use their own mu and sigma and convert it to a standard normal distribution. So how we find the percentage of a normal distribution curve? So this is what we can do. We can easily convert this normal curve into a standard normal curve and find the values. You will see why we convert this normal curve into a standard normal curve. If we have these two values a, b, you can use this transformation function or this equation and transform, or you can convert everything inside these two region, or inside these two values into this area. Okay, see, a becomes this value by using this one, b becomes this value by using this equation. See, b, which means at this point ux is b, so b minus mu over sigma. So when you convert this normal curve into standard normal curve, it doesn't change your area. Okay, this does not change your area or percentage, whatever. Okay, it doesn't change anything. Okay, so we convert this and do our calculations. Simply we can say, okay, after we do the calculation, we can say, okay, percentage is this much. We don't need to go back because it doesn't change. Okay, so I think you may have a better idea about this right now, how we deal with this kind of normal distributions. Anyway, hope you guys enjoy this video. I will continue this video series in future. So thank you very much and have a nice day.